Today's goal is to compare characteristics of polynomial functions. Characteristics such as x-intercepts, y-intercepts, who's positive, negative, increasing, decreasing, and so on. Let's take a look at our first example. A cubic function f and a linear function g are graphed below. Okay, so f must be the cubic function. It's got to be this guy. And g is the linear function. Okay, so it's got to be the line. Assume the x scale is 1. Okay, that tells us that this right here would be -1, -2, +1, and so on. Okay, approximate the solutions to the system f of x equals g of x. Well, solutions to a system of equations is a group of equations on the same graph, so that would be this graph here. The solution would be points where they intersect. So the solutions would be here, here, and here. So this would be -3.8, not quite all the way to -4, maybe -14.5. Here we're going just a little past 0, so maybe 0.2-ish, -7 it looks like. And there's one more point of intersection, maybe that's 0.7 or so, -3.5. You might have estimated slightly different places, but I am looking for approximately the coordinate pairs of these 3 points of intersection. Next, which function has a smaller x-intercept and y? Interesting. Well, let's take a look here. The linear function, we can't tell where exactly it intercepts the x-axis, but we know it'll be somewhere out here. And the cubic function has a bunch of roots, 3 to be exact. So which has a smaller x-intercept? Well, the cubic function. Since it has x-intercepts that are negative and g has only a positive x-intercept. I'll leave you to write the justification. Okay, next, this should be question C. Sorry about the typo. Which of the following will be true on the interval from 4 to infinity? Okay, so we're comparing f and g. That means we're comparing the y values of f and g on this interval. We know that 4 is an x value if it's given in interval notation. So our graph doesn't go all the way out there, but we can sort of imagine what's happening. This cubic function will continue to increase. The line will continue to increase, but at a much slower rate. So we're taking a look at this region. From the x value 4 and onwards, if we're comparing, well, both functions are increasing on the interval 4 to infinity, but clearly the cubic function is increasing at a much faster rate. So its y values will be much larger than the y values of the linear function. So we can say that f is going to be greater than g since its y values are bigger, since it's increasing at a much faster rate. Okay, next question. Example 2, the polynomial function f is given by the function -1 times the quantity x plus 5 times the quantity x minus 6 times the quantity x plus 2. The polynomial function g is shown in the graph below. Let's label that. The polynomial h is a quartic function, a degree 4 function, described by the table of values below, which is always increasing. Now, the last example I thought was easier because we had a picture. So let's see if we can draw a really rough sketch of these functions. If we look at the function f, I can tell it has 3 linear roots, so it'll have 3 linear x-intercepts. So let's plot them, one at -5, one at +6, one at -2. I would know that by setting 0 equal to the y value. And then solving this equation, that means I could set each factor equal to 0. That gives me the root -5 and so on. Obviously, setting -1 equals 0 is just garbage. It doesn't give you an extra root, but it does tell us that the leading coefficient is negative, so this cubic function is going to have this shape. If that -1 weren't there, it would have this shape. Okay, let's take a look at h. Well, let's plot its roots. It's also got a root at -5. Nice. And it's got really big y values before that. It's got a root at the origin and the y values are negative between these two roots. So we'll connect those. Ooh, the y values continue to be negative up until the next root, which is at 5. So it must bounce off, must bounce off the x-axis at that point, must have an even multiplicity, and then the y values get big after that. Okay. Now it'll be easier to answer. Which function is always increasing for x is less than -5? This is going to be a little bit goofy because we're going to trace backwards and forwards. X is less than -5 is this region of the graph over here, but increasing, we're reading left to right and looking for the y values to go up. So now let's go back to this place and trace along our y values. Here we see that the function g, already graphed, the y values are going down. In fact, they're going down even further until this sort of minimum point. For our function h, which is given by the table, again, the y values are going down. Again, they're going down even further than this root. Same is true of f, the function we graphed. The y values are going down. So in fact, this is not true for any of the functions, because all of them are decreasing on the interval x is less than -5, or on the interval from -infinity to -5, and even further. Okay, let's take a look at the next question. Which of the following best describes the product f of 7 times g of 7? Okay, well, let's see. F of 6 is 0. And f of 7, we don't know what it is, but f of 7 must be a negative number, because we see that the function is decreasing or going down after that root at 6. What about g? Well, g is increasing, so we're going to have some positive y value. So g of 7 is some positive number. We have no idea what that number is, but that means that their product, a negative times a positive, is negative. And so the product, f of 7 times g of 7, must be less than 0 or negative. Okay, name all the roots of the function f of x, h of x. Well, roots are x-intercepts, and we know that for an x-intercept to occur, that means the y value must be 0. So we're going to set 0 equal to f of x times h of x. And in order for that to be true, we have a product, right? We have some function times another function is 0, and that can only be true where one of these functions itself is 0, because 0 times anything is 0. So these are the roots of f, and these are the roots of h, right? Where are h's y value 0? Where are f's y value 0? Well, let's take a look. F has roots at -5, -2, and +6. So I can list roots actually either just by the x values, it's implied y is 0, or I could write these as coordinate pairs. And h, well, h has roots here at -5, 0, and 5. Again, I can list them. -5 I already have, 0, and 5. Again, I could list them either as just the x values or as the coordinate pairs. And if any one of these x values you substitute into f or h, either f or h will be 0, and 0 times anything is 0. So you can box in your roots. All right, last question. Which function g or h has a greater vertical stretch factor? How would you know? Well, that means g of x is a times x to some power, blah, blah, blah. In standard form, we're comparing their leading coefficients. That's what stretches the function up or shrinks it down. Okay, let's take a look at g. G is this function graphed. We don't actually have its equation written out. If g of x were written as some number times x to a power, we could just look at its number here and then compare that leading coefficient to h's, but we don't actually have the equation for either of them. So let's compare a point. Let's take a look at this function. It looks like g has this point here, which the scale is -100. Notice that there. So g has the point -130. I'm sorry, 1 -30, approximately. Whereas h has the function 1, negative 2400. I'm choosing the x value 1 because I have that y value for h. And if h has the point 1, negative 2400, this y value is a lot further from the x-axis than this y value is. So h has the greater vertical stretch. It's further apart from the x-axis.